All right, so today we are going to be studying something called the Madhava-Leibniz series, which looks scary, right? Especially if you're in like pre-algebra or algebra, probably seeing anything with Greek letters is pretty scary. I mean, there's perfectly good English letters. Why don't they use those, right? But but that's just what mathematicians do. But this is called the Madhava-Leibniz series. It's a way of calculating pi. We're going to be using it as kind of a goal for learning how to use for loops today. And I'm going to start by going over for loops after I just talk a bit about what we're going to do. What we're going to do is we're going to use this formula to do an approximation of pi. Pi, we kind of brushed on this last lecture, is a very magical number. It is a ratio. Specifically, the ratio of the circle's circumference to its diameter. And Wikipedia sometimes has issues, but for a lot of mathematically related stuff, for things that are mathematically related, computer science related, it's great. You see, the idea here, and I love this visualization. Sorry, let me go ahead and get it. This visualization is pretty great. The idea here is that if you create a unit circle, okay, basically a circle with a, with a diameter of 1, okay, and you unroll it, the amount that's unrolled is going to be around 3.14159. It's going to be pi, okay? So it's this ratio that makes circles work. Okay, it's what makes circles circles. Now, throughout history, we have needed various ways to compute pi. Okay, it's what we call an irrational number, which means that it's a lot of numbers. You can represent them as a fraction of some kind. You can't do that with irrational numbers. You can't encode pi cleanly, which is why you see it here presented as this series of numbers that never ends. And honestly, at this point, this is useful for most calculations. At this point, anything beyond becomes kind of bragging rights, and in fact, that's one of the ways you can measure kind of computing power, which is figuring out how many digits of pi you can calculate. But we'll go into that in a bit. The idea here is that calculating pi is kind of a tradition in computer science. We're going to revisit this later when we go over something called Monte Carlo approximations, which sounds like it's extremely advanced mathematics. And sometimes it is used in extremely advanced mathematics, but I like it because it fits my philosophy of liking to be really lazy with mathematics and just simply not do math because math hard. Like counting. I like counting instead. We'll just count. No math, only count. So, all right. So to review from yesterday, we were going over a for loop, and I'll be jumping into Runestone occasionally to basically show you execution of code. But for right now, I'll boot up an idle. Let's see, can I? Yes, I can. Okay, this may be the best way to do this. So let's go ahead and drag. We're going to go ahead and drag this window out. And we are going to drag this here. So now I can go from, we don't need you anymore. And that way, I can go from here. Whoops. That way I can go from here to here very quickly, if I just simply remember the key press command and don't miss them up. Awesome. Multiple desktops are a feature in most computers. You should probably try them. It's pretty nifty. The hotkey for Windows is Control Windows. Not sure what it is for Macs. If you need to, but occasionally you have to add a desktop first by hitting Windows Tab to bring up this screen and then create a new desktop. You can create an arbitrary number of them. And they're very useful if you like to use full screen stuff and you don't want to use up a lot of space. It doesn't work for everybody in terms of like I mean, it will work on the computer. It may not work mentally for you. I find myself not using it too often, but okay. Regardless, here we are. So I've got this file, and we're going to go over for loops today. So we're going to go to Documents, GitHub, Classroom, Intro, for Pi 130. Okay. So anyway, we learned of the repetition statement previously, which looks like this. It has two. It has basically two. It's made up of 4 fragments. Okay. It's made up of 4 fragments. 4x in y. Okay, and that's the way you'll typically read it. You'll read it like English. 4x in y. A lot of times we just simply the entire class on Tuesday we left it blank. We used an underscore to represent blank, meaning we didn't care what x was. We'll care a bit today, but for right now, just simply understand that the for loop is made up of 4 fragments plus the semicolon. The semicolon is always used to indicate to the computer, better prepare yourself, an indent's coming. So the for and the in are always there. They're always the same. They're always there. 4x in y, and you're always going to do that, and those aren't going to change. So the only 2 things that are going to change throughout the semester are the x and the y. For the entirety of this first lecture, and for a lot of what we're going to be doing in class for over the next couple weeks, the y is always going to be the same. It's going to be a range function, which generates a range of numbers. For instance, over here, I can use some just stuff that we'll get to later. I can say, hey, can you list out all the stuff in the range? And it will tell you, here's a list of, here's a range of numbers that's 10 long. It will always give me the same range. And we'll get into how we use that later today. But range, it generates a range of numbers. Okay? And this over here, the second item, the 4x in range, we're going to get into that today, but that's going to be used to say for each individual part of this range. Oftentimes, though, as we were working yesterday, a lot of times we don't care about that range. We don't care about what gets generated. We just use we just use the range to do a repetition, to say we want to do this some number of times. So if I wanted to say print, so if I wanted to do something like this, I could say print high. This will run 5 times because it's in this for loop, and we've told this for loop, hey, for blank in range 5, run it 5 times. So whenever you see something of this format, where you say, where we see 4x in range 5, in other words, for anything in range 5, you know that is going to run 5 times. Okay? And it specifically is going to run whatever has been indented into this loop. Okay? Now, the quiz that you're going to have on Tuesday in the next lab, in lab 3, is not going to cover for loops. It's going to cover the 2 questions that it's going to cover, and I've told the TAs to cover it before class, are variables and something from the turtle exercise that we did. Basically, hey, here's some turtle code, draw it. Right? It's going to be, so if you did Tuesday's exercise, it will be no problem whatsoever. And so, but no for loops involved at any point in the quiz on Wednesday. This is just simply trying to review some material to make sure that you're caught up to that before you start experimenting with using for loops in the lab. Got it? So today is just simply trying to get you more and more comfortable with for loops. And so we're going to go over some complicated stuff today, but it's more complicated than what you'll be doing in your homework. And I like that because it'll make things seem easier by comparison. So it will be one of those things where we're going to start easy and get progressively harder and harder. So if you feel like I really need to study this to really understand it, that's okay. Because I do like to increase in difficulty as this lecture goes. So anyway, 5. So we've got 5 things there. And it runs. It doesn't really change that much. I can change the number of variables we do. The range. To say, hey, print out 10 times. And that can get arbitrarily large. I suppose we should answer a few questions that you might be thinking to yourself. What if we run 0? Obvious result is, it's a fairly obvious result. We don't print anything out, right? A range of 0 generates no numbers. And what about negative, let's say negative 10? That's the same as 0. It's not going to do anything. There is no range of negative numbers, so it just kind of defaults to 0. Okay? It'd rather do nothing than just simply give you an error in that case. And again, this can get arbitrarily large, but at this point, if you do something like this isn't an infinite loop, but it might as well be, because I kind of have to interrupt the execution over here, and I'm having a hard time doing so, as you can see. And it's just going to keep going until it does all. How many zeros did I put in? A lot. All 100 million of these things. So that was great. Kill. Yeah, there we go. So that's what happens with that kind of thing. Don't do. I did it again. Okay, that was smart, Andrew. Yeah, but in general, if you have to kill a Python program, don't worry about it, because you had to save it to run it to begin with, so you won't lose anything. But it's not uncommon, especially as a beginner programmer, to write something that just goes on too much. Okay. One of the more common things we will do with a for loop is something called an accumulator, which is a pattern, as we call it. It's kind of just a common thing we're going to do. And what an accumulator is that you start with a variable outside a for loop, like an x over here. Well, let's call it total is equal to 0. And this is a very common, we're going to do this tons and tons of times. We're going to use this all the time today. And it just sits outside of the for loop over here. And then what we do is we modify the accumulator in this variable inside the for loop. What do I mean by that? We do something like this. Total is equal to total plus 1. Print total. Now, first, what this means is that this is inside the for loop, right? For blank in range 10. That means that this line of code is going to be run 10 times. Now, let's ask ourselves, what does this line do? It's a very common line that we use, so very good that we understand it. It says, whatever, we're going to take what's currently inside of total, we're going to add 1 to it, and we're going to store that in the box labeled total. It just happens to be the same place that we got our variable from. So so it's going to replace that value. So what we're going to see is that we're going to get 10. But let's go ahead and run through that, okay? And this is why, and this is just simply why I have this pulled up, because I want to show you that this tool is fantastic, right? Show code lens, right? And so it will run through each of these steps and say, okay, we've declared total for blank in range 10. So we're inside a loop, and it says, oh, you have a variable named underscore. Cool. Yeah, that's why we don't really use underscore. That's blank is to say we don't care about it. So what we see is that so we're going to execute this line the first time. Total is equal to total plus 1. Then total is equal to total plus 1. So we update total to 2. Then we update to 3, then 4, then 5, then 6, then 7, then 8, then 9, then 10. It runs 10 times. It keeps incrementing the value by 1 each time, right? Right? So it modifies it as we go. You'll notice that this is over here, that this is the blank here is changing. It's varying in value because it is a variable, even though it's a weirdly named one. But I often use blank syntactically to say, I don't care about this, please ignore it, right? So that's very useful when we're working on Python code. Or not Python code, it's on code where there's turtles and stuff where we don't care about variables. So let's start caring about it. So one thing at a time again, let's go ahead and instead of removing that, I'm going to do this. 3 quotes has 2 functions in Python. The first is you can use it as a multi-line string. Which is pretty cool. So some string quote is equal to quote, quote, quote. and this is how you make a string that spans multiple lines of code. Right? So I've just printed out this code as a string, right? So that's one use. However, you rarely use it for its intended purposes. Instead, a lot of times what we do is that we just do this, and that's it. We kind of create a string and don't do anything in it. In effect, what this does is that it's a multi-line comment. It's commented out the code. More correctly, we should just go through and put in a comment symbol in front of each of them, but that takes more time. So when you see 3 quotes like that, it's often a comment. Okay? So, for I in range 10, print I. Now so remember, the format of these for loops, and I'll put them up over here, is for x in y, right? For some x and some y. For right now, as I mentioned, we're often for pretty much this entire lecture, we are just using the range function. Like so, right? For x in range, some number. So over here, we can put something we need to for x. In this case, we are going to put in the value I. We often use I comes from a couple of different practices in previous programming languages. It refers to one of two things: I for integer, because it's going to be a number, or I for index, which makes sense when you get to arrays or lists. So for right now, it's going to make sense to think of it as for I an integer. And so for I in range, print I. So if we run this, let's take a look at what we get. In fact, let's go ahead and shorten this to 5 just to make it easier to read. 0, 1, 2, 3, 4. It prints out the numbers 0 through 4. When we ask for a range will give us the numbers from 0 up to, but not including that final number. That seems like a weird thing to do, and the reason we'll see later on is because it will make doing some math easier, and it will also make working with arrays / lists a lot easier. So it starts at 0. We start counting from 0. We go up to, but do not include 5. As a result, we have 5 numbers from 0 to 4. Up to, but not including 5. So the way this works is that it goes in order. It starts from 0, and then I starts at 0 during the first iteration for the loop. Then I becomes 1, then it becomes 2, then it becomes 3, then it becomes 4. It changes value. It varies in value. The variable varies in value. That's why it's a variable. It can change. So I is equal to 5. So this will enable us to do some really funky stuff with turtles as we go on down the line, but that is how that that's how that works. There's a lot of other stuff we can do with the range function as well. But we will tackle them as we get along. So we've gone from basically seeing how this was, a blank. We could fill in. We saw how we could potentially use an accumulator, and now we've seen that this varies in value. Okay, so that's enough of us to talk about this abstractly, and we're going to talk about pi now to give us a goal to work towards, and we're going to spend the rest of this class building towards that goal and seeing how things work out. I'll be referring back over here to basically show how the execution of that code will work slowly, but otherwise, let's go ahead and take a look at this. So now, as I mentioned earlier, it's an irrational number. And I mentioned that you cannot represent it as a fraction. That hasn't stopped people from trying. In fact, there are some very good fractional representations of pi. One of them is this is this formula 22 over 7, which is 3.1428, right? Remember, pi is 3.14159 something, 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 right? So that 3.14 there is accurate, okay? So there's been a lot of different ways to approximate it, and as the years have gone by, we have gotten better. This is a logarithmic graph, meaning that each big mark of the graph is 10 times bigger than the other. Basically, we've been able to get 1 decimal digit to 2, over here, as math was developing, we were able to calculate some minor amount of digits. Enough to do actually any heavy-duty engineering calculations that you might need, right? Then over here, as we hit Renaissance/Enlightenment period for different areas, you got bigger and bigger results. There might be some bigger bumps in here, as there might be a mathematician who discovered it and like their treatise just hasn't been translated. That happens. But as you can see over here, we kind of took a really big jump around the time computers became able to be used for stuff. And nobody actually needs to do this many digits of approximation for pi. It's literally just bragging rights at the moment. Okay. Let's see. Early modern mathematicians got 35 digits at the beginning of the 1600s, 126 digits by the 1800s. The record for the manual approximation of pi was 527 decimals in 1853. This is what a lack of a television does to a man. Okay, so yeah, there's a number of different ones. Some Egyptologists claim they use 22 over 7. There's a lot of different ones over here. Let's see. Chinese mathematician Louis Hu, I don't really know how to pronounce Chinese names, unfortunately, but he used he used geometry in the same way that Archimedes did to put one shape inside of another. Zhu Chongqi did this fraction, 355 over 113. That's one I particularly like in terms of approximation. The idea here was trying to get a number that you could record and write and use that to write down. 3.14159 and that's accurate up to there. That's a lot of digits of accuracy right there. That's, again, all you need for doing those big engineering projects back then. Okay. So in the Middle Ages, though, when they started playing around with a lot of math, we had, let's see, Madhava of Sangamagarama, an famous Indian mathematician, 1340 to 1425. And what happens a lot of times is that you have one mathematician who, because of the inability of communication to happen instantaneously and lack of translation, they'll do basically the same thing over different times. So you've got the Madhava-Leibniz series, because Leibniz, famous mathematician, came up with it himself in 1673, hundreds of years later. But hey, that's what happens. So they came up with this formula, which is better rendered as this, which calculates not pi. I mean, it does calculate pi, but it's easier to look at it this way. It calculates pi over 4. Okay? Pi over 4. And we write it like this simply because the formula is now easier to see this way. It says to calculate pi over 4, you do 1 minus a third, plus a fifth, minus a seventh, plus a ninth, minus, you can guess the next one, it would be an 11th, plus a 13th, minus a 15th, right? So on and so forth. What you're doing there, and it gets rendered into this form, right? But basically it's saying is that you keep upping the denominator by 2, right? We keep upping this denominator by 2. So we just simply increasingly add higher and higher odd denominators. So 1 over an odd denominator, and then we alternate whether are we subtracting or adding. So we subtract, then we add, then we subtract, then we add, and the idea here is that the more of these that we add together, the closer we're going to get to pi over 4. And so once we do calculate that, all we have to do is multiply by 4, and then that will give us an approximation for pi. This kind of series is called, as you can see here, an alternating series because it alternates between going positive and negative. Okay? And believe it or not, we have enough right now with what we've learned from for loops to be able to work on this, to be able to do this formula, to run this formula and see that basically it's not a very terribly good formula, but it is an accurate one. And what I mean by not terribly good is that it takes a while for us to run. Imagine it's a pain to try to do things by hand. Okay? So we can kind of represent these kind of things. We can do 1 minus a third plus a fifth minus a seventh plus a ninth. That's just math. And these computers are made for it. So the first thing we're going to need is this accumulator that we've talked about earlier, right? We talked about how we have this total up here, right, is equal to we're going to start at 0 because that's kind of our blank slate, right, for doing addition, right? And then what we're going to do is we're going to add things to it. We can see how to add things in a for loop. We did this just simply by adding 1 and 1 again, but we can do things like add I to this number. For instance, we can do what I referred to as what I talked about in 2168 and was actually talking about this morning, the triangular number series, which is 1 plus 2 plus 3 plus 4. We went over that last week, but we can do that by saying total is equal to total, and plus, rather than 1, we can say plus I. And this is the way that an accumulator pattern works. We have some number that we're going to be adding to, and we add to it constantly in the for loop. Okay? And it will give us this number 10, but that doesn't necessarily and I could show you print statements, but honestly, at this, once again, I find this to be much more gratifying to just go over it like this. So we're going to go over this into the code lens, and we're going to see how this works. So the variables, as we add them up, are going to show over here. We can see the execution of the code as it happens. So we set up total is equal to 0, right? Total is equal to 0. So now we come to the for loop, and we say we're going to run this for loop over a range of numbers. That range of numbers is 0 up to but not including 5. So we say for each number I in this range of numbers. So the first value is 0. So we kind of get an easy freebie over here where we say, okay, total is equal to total plus I. So what are we going to store in total? We're going to store total plus total, 0 plus 0. Easiest math problem ever, right? It's going to store 0 in total. Next, so we're done with that part of the loop. So now we go to the next number, and set I is equal to 1. Because we go 0, 1, 2, 3, 4. Making sense so far to everybody? We're going through this range of numbers. The range of numbers is 0 up to, but not including 5. So total is equal to total plus I. So total is currently 0, I is 1. 0 plus 1 is 1. So we're going to take 1, and so we're going to do this. We're going to take 1 and store it in total. And that just updated to 1. Next, we're going to go on to the next I. So we went 0, 1, now we're at 2. So now we're going to execute total is equal to total plus I. Total is equal to total, which is 1, plus I, which is 2. So we're saying let's store 1 plus 2 inside total. Right? That's going to add to 3, and we're going to store it in total. Now we update I to 3. we say, okay, total, we're going to store inside total 3 plus 3. That becomes 6. And then we're going to say, now I is on its last value, we're going to say total is equal to total plus I. Total is equal to 6 plus 4. And that's going to give us 10. We've gone through all the numbers in the range of 0 through 5, so we stop the loop. And we print out our final value. Okay? Did that make sense to everybody? Did that help explain matters? Yeah. Any confusion there? Okay. So, and if we think about it, what we just did isn't necessarily, if we kind of squint at it, it's not actually that different than what we need to do. We just added 1 plus 2 plus, we added 0, but we also did 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, right? We could do it to 7 if we needed to, right? We're just adding progressively higher numbers. So we can modify that to kind of do this, what we need to do. But how do we, so I guess my question is, the first question we need to ask is we can do this. 0 plus 1, so 0 plus 1 plus 2 plus 3 plus 4 plus 5, ... We can do that pretty easily. And we have this place to get to, right? We have to get to 1 minus a third plus a fifth minus a seventh plus a ninth, right? We have to get there. But making that jump all at once is going to just be a bit too much. So rather, instead of doing it like that, why don't we ask ourselves a question? Instead of doing this, adding numbers like this, can we add our numbers like this? 1 plus 3 plus 5. So instead of adding all the integers together in a sequence, can we add just some odd numbers to this? Now, some of you might be looking at this formula and say, that 2k plus 1 thing gives me it gives me a way to do that, and that's certainly a way, but for most of us, we're looking at that and go, math, no, stay away, right? So we don't want to do that. Instead, we're going to use features of Python to do that. Range, as I mentioned, is a powerful tool. And if we print out a range, if we try to print out a range, and that's what we're doing, just typing it into here at this bottom part, we're just printing out a range. If we try to print it out, it's not going to give us much. Except it says this, range 0, 10. Range 0, 10. If I put in range 5, it says, hey, it's a range from 0 to 5. What I did to list out all numbers earlier was I said list range 10. And that listed out everything. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, all the numbers from 0 up to, but not including 10. If I do that for 5, it gives me all the numbers from 0 up to, but not including 5. So now you might be looking at this and saying, can I play around with this? And the answer is yes, you can play around with that. Range is very flexible. The range says, when we use it like this, we're saying, give me a range of numbers from 0 up to, but not including an end point, right? Or a stop, as the variable's called, but an end point. Here, it's up to, but not including 10, but it could be any number, right? Some end point. Well, you can also define a start point. By default, we don't need to because starting at 0 is the most common start point. So we can do from range, but we could write it like this. So notice we did range 0 to 10. That's what changed over here. And it's saying, hey, it does the same exact thing over here. Range from 0 to 10. Sorry, range 10, range 0 to 10 is the same thing. In fact, range 10 is just a shortcut to say range 0 to 10, where we define a start point and a stop point. Make sense to everybody? With range, we can define a start point and a stop point. So over here, let's go ahead and just, I'm going to uncomment this bit out in a bit, but let's go ahead and show you. Print, so for I in range, better to see it in practice first, right? And if we look over here on the highlight that comes up, it says range stop, range start, stop, step. We'll get into that in a bit, but range, start, stop. So let's go ahead. 0 to 5, print I, it's going to give us 0, 1, 2, 3, 4, 5. If I say range 2 to 5, if I change that, it's going to say 2, 3, 4. Make sense? It's the start point to the stop point. Now, I very rarely use this. You're very rarely going to use the start point, but it's useful to know. And it, again, like I was saying, it's extremely flexible. -10 to 5. You can start in the negatives if you needed to. Now, you might be asking yourself, okay, if I'm given an arbitrary start point and a stop point, how do I know how many times it's going to run? How many times is this loop going to run? And this is where that weird going up to but not including comes into play, because we can easily just do some math to see how long it's going to run. We can say the stop point minus the start point is the number of times it's going to run. So this goes from 3 up to but not including 10. So it's 3, 4, 5, 6, 7, 8, 9. It's 7 numbers. 10 minus 3 is 7. Right? Going back to a previous example I had, from -5 to 10, or I think it was -5, so I think it was 5 to -10. Doesn't matter. So -10 starts at -10, goes up to, but does not include 5. 5 minus -10, subtracting a negative, remember that's adding a positive. So 5 plus 10 is 15. So this runs a total of 15 times. So it's very easy to kind of look, if you need to see how many times things run. So again, this range is very flexible. Now, as we were typing this out, we also saw this. It said start, stop, and then step. And this is where we're going to make our life a lot easier, because step is where we get really flexible. 0 to 100, and so start, stop, step. By default, step is 1. Whoops, forgot a colon. Very common mistake to forget that colon. And this prints out all the numbers up to, but not from 0 up to, but not including 100. If I change this from a 1 to a 10, we're going to count by tens instead. Make sense? Up to, but not including 100. So 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. Making sense to everybody? So so let's go and apply this now. We started here. So we're starting with 0 plus 1 plus 2 plus 3 plus 4 plus 5. We don't need the 0, so we can start by saying we want to start at 1 rather than wherever we're going. Right? And this would print out the numbers from 1 up to, but not including 100. Print out 99 numbers. So that's a way of saying that we have gone from, so now with this, we basically are we are now at 1 plus 2 plus 3 plus 4 plus 5. Okay? Where am I in time? Plenty of time. Okay? So we've got that. Now the question is, how do I go from here to just adding the even numbers? And the answer is add every other number. We're going to, if we did this, right, this would be the even numbers. 0, 2, 4, 6, 8, 10. That's easier to see than what I'm about to do, but it's not too much of a leap once you see this. Right? Going from 0 to 100 by 2s, 2, 4, 6, 8, 10. If instead I start at 1, I'm no longer doing the even numbers. I'm doing 1, 3, 5, because I'm starting at 1, going up to but not including 100. So here, we're now at this point where we go 1 plus 3 plus 5 plus 7. Make sense to everybody? So if we go over here to our, so let's go ahead and comment this out and now implement it into the actual code we're going to run. Okay. And that gives us 45, but let's go ahead and, so this gives us 45, which is what we expect, but we need to modify this now. 0, we're going to start at 1, go up 2, but not include 10, go up by 2s. We're going to, and we get 25. And why don't we go ahead and just kind of print it out step by step. Print. So what we're going to do is we're going to say print total, let's see, plus I. So if we do this, where we say total plus I, right, it's going to kind of, I'm just kind of showing what's going on here. 0 plus 1, 1 plus 3, 4 plus 5, 7 plus 9, 16 by 9, 25. We note that 16 by 9 plus 9 is 25, because what I'm doing over here is saying total plus I. Basically, what I'm doing is I'm going to be calculating this out in advance. Looks weird, but kind of so I'm going to run it and then we're going to break it down, because it will get more complicated, but the changes we make will make sense as we make them, right? So this runs 5 times, right? It runs for 1, 3, 5, 6, 7, and 9. So what we're doing here is we're taking total. We're saying, basically what we're doing is we're writing out this equation for ourselves. We're saying total plus I, the value of total plus I, in the first iteration, that is 1, is equal to total plus I. So we get 1 is equal to 0 plus 1, because 0 plus 1 is 1. So 1 is currently total. Here total is 1 plus I, which is 3. See here the I values 1, 3, 5, 7, 9. Everybody seeing that? And so 1 plus 3 is 4. 4 goes over here. What's 4 plus 5? That's equal to 9. So basically, again, we're just printing out this equation. Everybody see how that's working? We're just printing this out. So we're doing a pretty good job of adding 1, then 1, then 3, then 5, then 7, then 9. Now, it turns out it's not actually that hard to go from here to this. 1 plus 1/3 plus 1/5 plus 1/7. And notice that I'm not bothering with the alternating sums yet, right? I'm not doing that yet. That's something we can add on later, right? The entire idea of this is that we are starting from this and we are getting progressively closer and closer to our solution. Make sense? So here, it's not too hard to go from this to this, because all we have to do to go from here to here is that we have to add 1 over in front of everything, which in terms of doing this, that's not that hard. We can say 1 over, and that won't make it true for mathematics, right? But we can, right, the math doesn't math right now. It's not adding it, but that's effectively what we need to do. And if we just simply, but it's very easy to go from adding I to adding 1 over I. Make sense to everybody? Or rather, I might, we were here, and we want to, instead of adding I, instead of adding 1, 3, 5, 7, we want 1 over 1, 1 over 3, 1 over 5, 1 over 7. And to just do that, we just literally just add in 1 over. That's as easy as it gets, right? It's kind of one of those things of like, how do you do it? And then once you see it, you can't really unsee it and don't know how you didn't see it before. Okay? But of course, just adding it like this becomes a bit of a mess, right? So what we're going to do is we're going to say, what we're going to do is we're going to add this 1 over to our equation, and we're going to say 1 plus a third plus a fifth plus a seventh plus a ninth. Oof, that kind of gets a bit ugly looking right there with that formatting because of decimal points. So we're just going to go ahead and we'll go ahead and just simply scratch this part out. And we'll just simply look at it like this. Make sense to everybody? We might change that later. In fact, I can change it right now to this. Right, 1. Right? 1, a third, a fifth, a seventh, a ninth. Make sense to everybody so far? And then we get this random decimal value that we don't care about because it's not our objective. Make sense? So now we got to go and figure out how to get from here to 1 minus, and what we're looking at actually is kind of something like this. We're adding the first one, subtracting the second, adding the next one, and we're just alternating between them. Okay? Every other one, we're alternating between them. So now we could, so those of you who have done programming before are probably thinking of a higher level solution than we need to, which is to use an if statement. Basically, that's a way to make decisions and say, hey, if this is true, do this, otherwise do this. We don't really need to tackle that. Instead, we're going to use, once again, math to our advantage here, which is we're going to use that little trick in mathematics, which is that a negative times a negative is a positive, and a negative times a positive is a negative. We can basically use -1 to flip a switch. In fact, what we can do here is we can say something like this. We can say numer for numerator. Okay, makes sense to everybody? And then we can do something like this. Denom for is equal to I. I know that seems weird. And we can just simply write everything as a fraction by saying numer divided by denom. And I'm just making it 5 letters because it's just easy. And notice it doesn't really change anything over here. We're still getting the same answer. I'm just simply giving it what I'm doing over here is I'm essentially giving I another name tag, right? I is some value stored in memory, and we've given it a name tag that says, hi, my name is I. He's also got a second name tag that says, hi, my name is Denom. And I'll answer to both names. Now, this numerator doesn't change right now, but what I'm suggesting is that we can change it after every single, right? If I do this, numer, right? We can say, hey, 1, 1, 1, 1. And this is not changing. It's always positive 1. What I'm suggesting here is we can change this. We can say, okay, we've added our total up. Total is equal to 1 plus the numerator over the denominator. And then we can say numerator is equal to the numerator. And rather than adding a value to it, we're going to multiply. Because if you can add, you can multiply. There's no reason why you can't do that. You can change it like that. Times -1. Right? And now, if we run it, we get 1 plus a -3rd plus a negative plus a 5th plus a -7th plus a 9th. Make sense to everybody? One way we can also rewrite, now this doesn't have to be the only way to do that, by the way. I could have totally wrote it out in a different way, and this may may make more sense, where I take kind of the same, and I'm keeping it here. I'm just keep the same loop. Okay, but right, and I can just simply skip stuff and say 1 and just rename it. And none of this denominator stuff, numerator denominator stuff. It is just simply 1 that is switching value. Make sense? And both solutions are equally correct. Both are equally correct. Which one you arrive to just simply depends, right? This has involved less changes, but in the end, we get there. Now, our total is 0.849206, and I don't know what pi over 4's value is, right? I doubt you do as well. I don't think you go around randomly memorizing fractions of pi. It's a weird hobby if you do. But this calculates pi over 4, right? This formula is equal to ... is equal to pi. It converges to pi over 4. So to change this from pi over 4 to pi, we just multiply by 4. Make sense? It's pi divided by 4, and if we multiply by 4, that undoes the division. So let's see what we got. We got 3.39, which is, well, at least the first digit is right, but supposedly this is supposed to give us pi, right? Well, as we add more variables is the idea. The idea here is we add more and more values to eventually get to pi over 4. So what if we did 100 terms? Right? So, and that gets us 3.12. Now, one of the very interesting things I find interesting about this formula is import math.pi, I believe. Copy this value, paste this value. 3.141592. 3.12159. It's a very interesting thing that happens where basically that some of the digits that follow are correct. And basically what's going on is that we get some amount of this amount of pi correct, and and what this addition or subtraction is that it's fixing this bit, but then affecting a later digits down the line. And so it's attempting to become more and more accurate. Now, this is doing 100, and it looks like that's closer to pi than 3.33. And at this point, we could go to 1,000, right, and up it, but this is going to take a while, right? So it turns out that printing is a fairly expensive operation because it requires updating your screen. Some computers can do it a bit faster than others, but idle, or some programs I should say, idle's fairly slow about it. So how do we get around that? When you're ready, remove your print statement. Just don't print as much. And you'll notice that it runs a lot faster, nigh instantaneously, right? So 3.13 as opposed to 3.14, okay? So let's go ahead and do that 100 times more, or a magnitude of 100 times more. So 100,000 times. 3.141572. So now we can see, let's look at math.pi again. So, yes, because this is a completely different program, so I have to import math again. You know what? Actually, let's go ahead and add this to our script over here. Usually what you want to do is import math at the top, but if you ended up doing an import statement otherwise, that's fine. Math contains all those icky math functions that you don't want to do, or maybe the ones you really like if you're like me and you really like math. Um, just so you understand, I took, I was offered different quote unquote packages, threads as they were called during my undergrad, to kind of choose which selected my electives. There were different elective packages for my upper level classes, and I was not confident as a programmer, so I chose the math heavy ones. Because I thought that the mathematics was easier than the programming because I had like no self-confidence as a programmer. Typically, we're much better programmers than we think we are if we get out of our own way. Imposter syndrome is real. So what we'll do is we'll import math, okay, and we're going to print out math.py underneath our result. So that we can compare them. So here's what we have. We have 3.141572. Let's actually go ahead and just run it up here so it's easier to see, right? So here's our approximated value of pi. Here's actual pi. And you'll see we've got a match here and a match here. That's a pretty big match. And what we're missing over here is that 9, right? 100,000. Let's go at 100,000. Sorry, no, we were at 100,000, a million. So this is going to be adding or subtracting the fraction of 1 over 999, comma 999. And that, so as we do it, it gets more and more accurate. And a modern day computer doesn't even break a sweat at doing this a million times. 10 million times? Well, that a million times actually, there was just the briefest pause. The briefest pause when I did a million times was almost undetectable unless you're looking for it. So if I go to up to 10 million times, right, that's what this is, 3, 2, so it's 10 million. Well, it's got 10 briefest pauses, so to speak, to do. So it's going to take 10 times as long. And if I go up to 100 million, that is going to take, 10 times as long. Now, there are ways to kind of get around this, sort of, which is you could use multiple computers to do multiple portions of the formula and kind of spread out the work with this. You can also just use a better formula because, again, this one was invented before computers. And honestly, not that bad for that. It does the job after a fashion. And as far as why this works, it's the proofs are there for you. If you're interested, they require calculus, as you can see, and the unusual behavior that I noticed about how you got a lot of matching digits, but there's only a subsection of digits that are wrong. Also, note that basically there's a limit to even when we print out math.py, it's not going to print out all the digits of pi, right? Or not even like an absurd number. It's going to print out quite literally as many as it can hold, which is determined, as I mentioned, by these floating point numbers, right? These right? It can hold 64 bits worth of data, and this is about 64 bits worth of data over here. But again, at this point, once you get beyond this point, right, this stuff over here isn't needed for like a lot of calculations. And when you do need it, you'll know you need it. But for like doing your homeworks and stuff, this is going to suffice. Let's see. Wow, this went much quicker than it normally does. So, any questions on this approximation for pi? Yes? more caching, I would say. It's just continually doing additions and additions. It doesn't really need to store it in memory. Sorry, it doesn't cache the CPU. I would think. I mean, it's an interpreted language, so I can't really. I'm kind of guessing here, but I mean, this RAM is slow and storage is even slower. The entire point of a lot of things of a lot of efficient programs is to try to avoid. Or efficient memory calculations is to avoid that RAM as much as possible. Or RAM is slow in comparison to what the CPU stuff right there. Yes.
A question about range function.
Yeah.
Can you do step that isn't float?
Can you do a step that isn't?
A float.
Can a step be a float in range? Okay. So yeah, let's go ahead and take a look at range. That's a great question. So abstractly speaking, range can do a lot of stuff. Range, though, let's go ahead and just first look at 1 to 10.0. See if we even, in fact, let's just look at range to 10.0. It's not going to like that. Make sense? So makes sense that if it doesn't like it as a stop point, well, what about as a step? 0 to 10 by 1.0. Doesn't like that either. So range is integers. Make sense? Now, that being said, it doesn't have to be positive integers. If you want to go up, if you want to go backwards, you can. 10 to 0, it's going to just tell you, so if I do 10 to 0, right, what is it going to do? It's going to say, hey, list range 10 to 0, just to kind of show you. It's going to say there is no range of numbers from 10 to 0, right? That's because we're going to be counting up, and I can't count, and the default step is 1. However, if we change this from a range of 10 to 0 to negative 1, it's going to give us 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's going to go from 10 down to, but not including 0, right? It's the same language that we use. 10 down to, but not including 0 by negative 1s. And so once again, we can use the same formula that same trick to figure out how long it was. The endpoint minus the start point. Endpoint minus the start point. 10. And negative 10, yeah, it's negative, but it still works to give us the magnitude of it. Now, one thing I did not mention that I typically do mention is that when we write, if a range, mathematically speaking, is, you've probably seen this in algebra a bunch of times. If you're taking algebra or pre-algebra, right? Algebra or pre-calculus, right? When you're doing graphs, you've probably seen like this notation, right? Where, and basically you're saying this is the numbers 0 to 5, right? And these are the numbers from 0 up to, starting from 0 and to 5, but not including either endpoint, right? That you've probably seen that notation in algebra. So what a range function is that it's doing this. Include the start point, exclude the end point. Okay. So that's another way to think of it if you need to remember how that works. Other questions? If there's no other questions, my plan is I was going to go over just a bit. I was going to go over a few hints for the lab and the homework rather than just straight up dismissing you, because we have time and might as well give you as much help on your homework as possible. Okay. So this is currently week 3. Just a heads up, we typically do our exams on week 6, right? It will be either end of week 5 or week 6, depending on how it's timed out. But the entire point is that you'll see Lab 3 is worth 100 points. Lab 2 was worth 100 points. Lab 4 and 5, because you'll notice that I placed them together, because we go over we cover 4 loops that much, is 2 weeks worth of labs, right? And it is, and that is 180 points, right? So it's almost, but not quite 2 labs. So just a heads up about that. So the turtle loops I kind of talked about. So let me go ahead and just start a new Python file. So we've got these various functions. I went over them last time. And let me just kind of give you some good notes for what you need. First off, if you need a reference to what you can do with turtles, there's 2 places you can look. First, you can go over here to the textbook, and if you check your readings, it had chapter 5 listed as a reading. That's because we go over a lot of the stuff in this chapter. Right over here, a bunch of different things you can do with turtles. This is not exhaustive. The exhaustive list of things you can do with turtles is turtle docs Python. The document page, docs.python.org. And this goes over everything you can do with turtles. And it has a list of basically all the functions, and you can click and see what they do. One of them is that the main one to take a look at for problem 1 is circle, which we kind of introduced there. And when you see something like this, where it says turtle.circle, and then it's got one argument, the radius, which is what we used last time, but then it's got extent and steps, that means those are optional parameters. So let's go ahead and take a look at what those do, because this will help you. Okay. So new, save, HW3 hints. Okay. So once again, what we're going to do is we're going to import turtle. Again, the magic line, you need that. We're going to say Bob. You can name it Alice. You can name it whatever. I just like Bob because it's 3 letters, and 2 of them are the same. So turtle.turtle. Okay. And what we can do is we can simply say, let's go ahead and see what he does. Bob.circle 200. This will make a circle with a radius of 200. Okay, a bit bigger than I needed for the screen, right? It's fine drawing outside the screen. So let's go back to 100. Okay. Now we had some other arguments, extent and steps. Extent gives us, well, let's plug in a number. I know what it's going to do, so I'm going to plug in 180 just to kind of show you. And extent gives you that. It did half a circle. It did 180 degrees worth of the circle. Remember, a circle's got 360 degrees to it. So 180 gives you that much. So you can actually just do a small portion of the circle. You can do something like 350 degrees and do almost all of it. And if you're drawing some rings using this, we might as well do, let's see, turtle.width or pen size. It does the same thing. Bob dot pen size, and let's do 3. We can make the width of this pen a lot bigger if we need to. That's how many pixels wide it will be. Okay, so that might be useful in regard to making the rings a bit easier to see. Okay. And then the last bit, which is not necessarily useful for this part of the assignment, but I do like to be a completionist, right? Let's say 360 degrees. Let's do 8 steps. Oh, well, you look at that. It's doing what we did on Tuesday's lecture. It says this is how, right? We remember what Tuesday's lecture was all about. You can't draw a circle, really. All you can do is draw a polygon that looks like a circle. That's what this is saying. It's saying, wait, you can manually define that the number of sides that polygon has, right? And here's a 100-sided polygon, a 100-agon. And again, that looks very circle-ish, but the idea here is that Python should automatically be able to kind of figure out how many you need, okay, in order for it to look like that. And if you need, and again, this is extremely flexible, right? And he'll just simply, you might be able to see him, but he still goes around multiple times. Now, why am I talking about this, right? So my advice for the first problem, okay, and this takes a lot of trial and error, again, is rather than making one turtle and having him draw everything, right? Because then you'd have to figure out where he's got to move. First off, the turtle starts drawing it from the bottom of each of the rings. That's fine. But we'll also create an Alice is equal to turtle dot turtle. And let's go with a Carl maybe, right? Is equal to turtle dot turtle. And, you know, I could make Alice dot color red. And then what I'll do over here is I'll say Alice dot left. Actually, I don't need this. I can just simply say Alice dot forward 200 and run it. And you'll see Bob's going to draw his circle. Alice goes, and then Alice will go forward, right? So it won't run these things at the same time, which you don't need it to do that. But you can have each turtle do a different job. So the idea here is that you get each turtle into position, have them each draw a ring of the same size, right? And then look at it and say, I need to scooch these guys over a bit more, or I need to scooch these guys a bit up, right? And then rerun it. Remember, to move them into position, if you need to move them into position without drawing anything, using the up command, right, means they won't draw anything. Okay? Right? Here's Bob. He's doing his loop-de-loop. He's very happy about doing the loop-de-loop. And now Alice moved forward and she didn't drag your pen along. Just remember, you want to do pen dot down, because if you don't, you won't draw anything. Bob dot up. Right? And so he can go in a circle all he wants. He just won't draw anything. Okay, so you want to use your ups, downs, and your circles to get in position. And again, if you kind of have an idea of where you want your turtles to go, like if you planned it out on graph paper or something like that, my friend who works for Google and makes ludicrous amounts of money now, he is a very big believer in the basically don't immediately put your, especially if you're just beginning out, don't put your hands on the keyboard. Take out a piece of paper and plan things out first. He's a very big believer of using paper to kind of plan out what you're trying to do. So plan it out on paper. You figure out where they want to go, and you can, instead of trying to navigate them left and right and stuff, you can just simply say Alice.goto, and you can tell her what position you want her to go to. Remember, it's a Euclidean plane, so if I tell her 150, 150, she's going to go there. Right? And now Alice moves to x is equal to 150, y is equal to 150, right? This is just a grid. This is just an algebra. This is just a grid from algebra. You're familiar with these. This isn't scary. It's just moving to x, y positions. There's no slope involved, no having to calculate a slope. You just say, this is where I want you to go. Or if you don't want to do that, you just tell it turn left, turn right, and tell it to go to that position, or tell it to move forward. And no, you don't have to worry about, whoops, I don't need to shout your name. If you just turn left 180 degrees, or whatever, yeah, why not? 142 degrees, doesn't matter. Right? Alice is going to turn, and then she'll move. Right? It doesn't care, right? The orientation of the turtle doesn't care. Go to just kind of drops it in that, will make it go to that spot. It won't drop it there. You still got to have your pen up, because if you don't, let's go ahead and just simply say, you'll still draw, right? But you get the idea here. It's just a matter of, you've got a lot of controls at your hand, at your ready for this one. Okay. So the other ones are a bit easier to go over. especially since most of the hints apply. For this one, turtle clock, my suggestion is this one, definitely make 5 turtles. Here, you probably don't need to make 12 turtles. Instead, what you do is you use 1 turtle and you have him move forward. You have the turtle move forward with his pen up, then put his pen down and move forward a little bit, then put his pen up again, move forward a little bit, and then use stamp to do a little ink belly flop. That's what stamp does. It basically does a belly flop of a picture of that. Then you have the turtle move backward while his pen is up still. Have him move backwards the exact amount that he moved forwards. If you do that, guess what? He's exactly in the same start position that he was in previously. Then you have him turn a little bit. And then just put that in a for loop that runs 12 times. Make sense? You can, of course, copy paste it a few times to kind of see are you getting to the right place. But the idea here is that if you find yourself copying and pasting a lot, it's probably meant to go in a for loop. This one, if you're lucky like me and have A as an initial, the A is going to be fairly easy to draw. If you're unlucky like me and have an R as an initial or a B, then those curvy parts might be a bit hard to draw, but try using the circle to kind of do a bit of that over there. You can also, again, use like blocky text if you really want to, right? There's nothing stopping you from doing let's just pull up Paint because that'll be quickest. Right? All it cares about is that it's legible. Right? So if you do your R like this, let's see. No, that's not a good R. Right? R's look like this. So if you do an R kind of like this, that might work. The point being is that, or even better, a D looking kind of like this. Fine, I'll take it, because otherwise you have to do something like that. But the point being is that it's not necessarily too scary to do. Number 4, if you were keen-eyed, right, well, hint out over here, check out runestone.academy, and the link is to the base textbook that we use, the base textbook that I use for our class. And if you look at that, that's the exercise we did on Tuesday. And if you're keen-eyed, you might realize, oh, this one is basically a freebie. If I did Tuesday's lecture. Finally, the last one, and then you can go. I was wondering where my tab went, but there it is. The Triforce. Again, that one's just trial and error. Again, it's an equilateral triangle. Or 3 equilateral triangles, or equilateral triangle inside an equilateral triangle. It's all equilateral triangles all the way down. So each of them is worth 20 points. And again, the extra credit for overlapping and correctly weaving the turtles with the correct colors, that is worth 10 points. So, all right, I hope you have a great weekend. Take care.
We're not live. Can we